He wasn't here.
Sorry, Deacon, we're going to catch you up real fast. So, if you have, this is representative of 1 mole, 22.4 liters at standard temperature and pressure. So, if you have 1 mole of any gas, how many particles are in any mole of any substance? 6.02 times 10 to the 23rd.
Hey, I remember this point.
Now, the reason that it is that number, and here's the reason why. If you look at the relative atomic mass of a nitrogen molecule, which is, each one is 14, multiply that by 2, you get 28 grams per mole. So the reason that it's 6.02 times 10 to the 23rd, literally, this is what they did. The initial understanding of chemistry and how the periodic table was arranged was based upon relative atomic mass. Because at the time, in the late 1700s, early 1800s, there was no concept of protons, electrons, and neutrons. They had no idea of s orbitals, p orbitals, d orbitals. Okay, you had nothing like that. The only thing they could base it upon was properties, how they reacted, and relative atomic mass. Okay, so they had those values. So basically, this is what they did. They said, okay, we know they couldn't measure out the mass of one nitrogen atom, okay, or a nitrogen molecule. It's just impractical. I can't take a sample of nitrogen gas, reach in here with a pair of magic tweezers, pull out one nitrogen molecule, put it on a scale, and go, oh, there's the mass. Okay? Can't do it. Impossible to do. So what they did is they said, okay, we're going to never deal with individual molecules. So this is the thought process. They took the 28 atomic mass units, which was the relative atomic mass. They took AMU, they marked it out, and they said, we're going to call that grams. They could have used kilograms, which is actually in physics, instead of moles. It sounds weird. We use kilomoles. And instead of 1 mole being 28 grams, it's 28 kilograms. So in physics, this will be later on. Once we get into some calculations, we'll say 1 mole is 28 kilograms, which means Avogadro's number is 6.02 times 10 to the 26th. Okay? But for now, just go with the chemistry definition. Don't make that shift until I tell you to. Okay, for now, when you're talking about a mole, go with the chemistry definition. Okay, it's the relative atomic mass in grams. So literally, they said, okay, we're going to call this grams. So the next question was, so if I take a container and I begin to add nitrogen molecules to it, the question is that I put this empty box, it's in a vacuum, I put it on a scale, and I begin to dump in nitrogen gas. At what point, how many particles do I add when I find the mass of this box again? It equals 28.0. And if you count the number of particles that you had to put in, that's 6.02 times 10 to the 23rd. There's nothing magical about the number. If they had said, oh, hey, we're going to make this 28 pounds, Avogadro's number would have been completely different. Because instead of 28 grams, you had 28 pounds. Avogadro's number would not be 6.02 times 10 to the 23rd. So the only thing magical about 6.02 times 10 to the 23rd is that's how many particles it takes to have the combined mass equal to the relative atomic mass measured in grams. Okay? That's it. There's nothing magic about it. So, what that tells you is that each nitrogen molecule is very, very, very small. So, if I want to find the total charge on all the electrons in 1 mole of nitrogen gas, okay? So start with this. This is just a conversion problem. You have 1 mole of nitrogen gas. 1 mole of nitrogen gas is going to contain how many molecules of nitrogen? 6.02 times 10 to the 23rd molecules of nitrogen. Now, each molecule of nitrogen contains how many electrons? 7 or 14? 14. Okay? So if I do this calculation right now, if I stop right now, what would my answer be? Number of electrons. Okay, it's a big number, right? So you're taking 6.02 times 10 to the 14th, or times 10 to the 23rd times 14. That's going to be a big number, right? But that's not what I want. I want the total charge. Now, this is what we talked about earlier, that each electron and each proton has a charge of 1.60 times 10 to the negative 19th coulombs per electron, or per proton. So now the last step on this calculation, I ran out of room, is that down below, I'm going to put 1 electron. So if I have 1 electron, and a marker that I can't get rid of electrons, ironically. So if I have 1 electron, what's the charge on each electron? Well, 1.60 times 10 to the negative 19th coulombs. So if you want the total charge on 1 mole of nitrogen gas, you're just going to start here. Oh, there's 6.02 times 10 to the 23rd. 1 molecule is 14 electrons. Each one has 1.6 times 10 to the negative 19th. This is straight multiplication. So, Sean, what do you get?
Like 1.35 million. So 1.35 times 10 to the 6th.
Times 10 to the 6th coulombs. Okay? Now, what you'll see is that that's actually a lot. Okay? So that's the total negative charge on 1 mole of nitrogen gas. What would be the total charge on all of the protons? Exact same number, right? Because that's also going to be 1.35 times 10 to the 6th. So the total charge on all the protons is going to equal the total charge on all the electrons, which is why overall we're electrically neutral. Now, let me go get a balloon and a blanket. I'll be right back.
This is one of the things where we need to do things.
It was not. So I thought it was pretty.
Well,
Yeah, it was. You just had to like not be done.
You're not wrong. Yeah, yes, he is. Yes, he is.
okay.
Okay, so Andy, give this a spin over. Give that a
That page at the bottom, the KSP, just the final two. Yeah.
Okay,
And the limiting reaction.
so if I take my hand
Yeah.
and put this up here, what's going to happen? Is there a gravitational attraction between my balloon and the hand?
Yes.
Enough to make any difference?
No.
No. Now, but if I take the balloon and rub said balloon,
Yeah.
right? Now I bring my hand near it, come on. Now I can make it move.
How did you make gravity stronger?
Oh, I'm a Jedi. So, here's the story. So what do you know about like charges? They repel or attract? Repel. Okay? Unlike subtract. So, when I put my hand here, and there's nothing actually about my hand. So I put my head here, okay? That's the same thing. It isn't just my hand. It's anything. I can even do my arm, okay? All right? So, basically what's happening on an atomic level, when you see an attraction, there's two possibilities, okay? One option is that my hand is actually positively charged, okay? That's an option. So if we assume that the balloon is negatively charged, and it has excess chihuahuas, if that's negatively charged, one option is that my hand is positively charged, and that's going to make it move towards it, okay? do you think that's an option that overall I have a positive charge? No. Okay? No, it's like I'm walking down the hall like, oh, we're against positive today. Okay? No, we're neutral. Okay? Now, are there a whole bunch of charged particles within us? Yes. But overall, we are neutral. So, the other option is that if you look at the surface of my hand, so, and here's my thumb, okay? And there's the balloon. So here's your other explanation, is that if you assume that the balloon is negatively charged, okay? Then what happens is that when I bring my hand up close to it, the chihuahuas that make up my hand go running away. They're like, we're out of here, okay? Because the chihuahuas in my hand don't like the chihuahuas there. Anybody have a chihuahua, by the way? Okay, right? You know exactly what I'm talking about, right? So these little yip, 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 yip. Okay? So there's a bunch of chihuahuas there, and the chihuahuas in my hand are going, we're out of here, we're going to Taco Bell, we're making the run for the border, those chihuahuas are out. Now, what's left behind are the St. Bernards and the sheepdogs, because they're like soft, okay? They're not going anywhere. They're just chilled out. So the chihuahuas say, we're out, they leave, they're gone. What's left behind? The positively charged St. Bernards. Do the St. Bernards like the little chihuahuas? Yeah, they do, because they're oppositely charged. Okay? So the St. Bernards go, dude, okay, the chihuahuas have left. We like the little buddies, okay? Like, come here. So the St. Bernards that are left in my hand make my hand, very small regions of my hand, positively charged. So it isn't like they completely leave. All that's happened is that enough of those chihuahuas, because they're little chihuahuas and they can move around easily, those chihuahuas move, and what's left behind is enough of a charge that this becomes attracted to my hand. So when you see something attract, there's two possibilities that could happen. One is that my hand is actually positively charged. That's an option. The other option is that when I do this and I see it move, I temporarily induce a positive charge in my hand because the electrons run away. So if I do this, then I take the other balloon, this, okay? Now what happens? Oh, the chihuahuas don't like each other, okay? So now you have two equally charged chihuahua gangs, right? Now, the only way, and here's the difference, the only way you can get a repulsion like this is if they have the same charge. You can't, that's the only way. So attraction is like, there's two options. Either my hand is oppositely charged, it's positively charged, and it's attracted, or the other option is that my hand is temporarily positively charged because the chihuahuas ran away. So when you see something attract, there's two options. It's positively charged, temporarily because the chihuahuas left, or it's just the complete opposite charge. But the only way you can make two things repel each other is if they have the exact same charge. So you attract, there's two options. Repel, there's only one. Now, here's the deal. Because these two don't like each other, what's actually creating this, and this is what's called action at a distance, okay? Because if you notice, these balloons aren't actually touching each other, but yet they're being repelled. And this is what gets really weird. It's like, okay, well, what's doing that? What's actually doing that is an exchange of photons, okay? It's the same photons that carry light. So this electric field is being carried by these photons. The fields don't like each other, the electrons don't like each other, and they push each other away. So static electricity is actually carried by photons, but then you get into real photons versus virtual photons, and it's really, really weird.
No, please continue.
No, it's okay. No, because that's a whole other discussion. All right, bring yonder camera. We're going to the back.
You have to look at gap showing.
No, once I'm done, I know.
All right. So, let's start with this little gizmo. So, if I touch both sides, I complete a circuit, okay? Which means that my body has the capacity to allow a circuit, a flow of chihuahuas to go across. Now, you hold that side. Now, touch my hand, okay? So what's happening is that Jaden and I are completing a circuit because of the fact that that electric field is going all the way around. Now, we're going to have a kumbaya moment. I want to form one big circle, except for Danny. Danny's just going to and we're going to hold hands. Okay?
You're not allowed in the circle.
Okay. All right, so we got to touch all the way around. Okay, right? Now, Jane Carroll, let go of Laura's hand. Now, just touch her finger. Now, just like, literally, just go like, boom, 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 boom. Okay? So here's the cool thing. So this electric field is going all the way around us, okay, this entire room. And so, do this again, okay? So, this senses, even when Jane just touches her hand, the light electric field is being completed. So those chihuahuas have the capacity to flow around all of us because we're all conductors of electricity. Okay, got that. Now, this is a Van de Graaff generator. And so what this does is that it does what I did with the balloon, but like on steroids, okay? So I'm going to put this up here, and come on, stay here. Settle.
I did that before my test today.
You did what? I don't know yet. Okay, so we'll turn this on.
Magic.
Okay, so very quickly, what happened? Magic. Okay, well, they're charged. Okay? We don't know if they're necessarily positively charged or they're negatively charged. We know that they're charged. So if you assume that this was creating a dome of negativity, then this has excess electrons, right? So when I put my hand near it, I can get that exact same effect of what I saw with the balloon. Why? When I put my hand here, let's assume that these are negatively charged. So when I put my hand here, what happens? The electrons in my hand move away. The St. Bernards are left behind, and they're attracted, right? But here's how. Let me fire this up again. Hold on. Hold that. Every time I've done that in my entire life, you just never get used to getting shocked. Okay, so let me turn this back. Okay? So, if I rub the balloon,
I'm not going to touch it.
okay? and I bring the balloon towards it, what happens?
Yeah.
It's attracted. So what's one possibility that these are attracted to it? To describe what is happening. The balloon could be positively charged, or at least the opposite of that, or the balloon could be neutral. The balloon could just be neutral. It would be just like my hand, right? So if I bring this close and we see an attraction, one option is that either this is neutral and you induce a small area that's positively charged, or the balloon is actually the opposite charge of that. Okay, so let me do another test. So I'm going to fire this up again. Come on. And charge up the balloon again. Turn this on. So, what do you notice is happening with the balloon when I bring it close? It's attracted. Okay, now, if you assume that the balloon is negatively charged, okay, if you assume the balloon is negatively charged, what has to be the charge on the Van de Graaff generator? Positive. That has to be positive charge. And that matches the observation that when I put this on here, okay, when I put that on there, and I turn that on, so when I brought that balloon near it, these are actually attracted, not because the balloon is neutral, they're actually attracted because they have opposite charges. Now, to prove that there's a field, okay, and you guys are the first AP Physics students to ever see this demonstration.
Yes.
We
My
special.
honors physics class saw this earlier in the year. But you're the first AP Physics class to see it. So this is just a bubble solution. Oh, back here.
They're supposed to get this first.
You did.
Somebody wasn't paying very much attention.
Okay, so make some bad symmetry. Okay. So what do you notice about the bubbles when it gets near the Van de Graaff generator? Absolutely nothing. Okay? There's nothing. Okay? There's no trick questions. It's just nothing. Right? But if I turn this on,
What?
It's a bubble force.
so what are
You don't even like
Find a way.
so they're repelled. But
It's a bubble force.
hold on. But if I discharge it and I do that, what do? They just
Nothing.
nothing. Okay? Charles with the nothing answer.
Oh, yeah.
Solid on nothing.
Oh, yeah.
Okay. So what changed when I turned it on?
The Van de Graaff made in the electric field.
Yeah, so obviously there was a field that was being generated, but it was repelled. Okay? So it wasn't like they went boom, right? The balloons, the bubbles were repelled. So what does that tell you about the charge on the bubbles?
They're positive.
They're positively charged, okay? Or at least the same as whatever this is. So what was happening with the bubbles was this. Let's assume this was positively charged. So if that was positively charged, if we modeled this as being the bubble, okay? So as that bubble began to get towards it, if this is positively charged, what's going to happen to the chihuahuas? So if this is positively charged, okay, it's a deficiency of these, right? So there's a lot of positive charge. So that means that on this side of the balloon, the electrons are going to be moving towards it, right? So that means you're going to have, within the balloon, you're going to have a positive and negative region on the balloon.
Oh, polarization.
Oh yeah, it's just gonna get polarized. So because of the strength of that electric field, the soap bubble is gonna rotate a little bit. And so as it rotates, it's a dynamic situation. Once that like charge of that soap bubble gets near it, it's gonna repel and it's gonna go flying away. So what this is doing is showing us that there's an electric field. We can't see it. Our eyes can't pick up electric fields, but that's present, that's indicating that, wow, there has to be something there. Now, I can also take this and this.
We're around the kind of go school love because, oh, look, it just happens to be no matter which can be polarized.
Do a barrel.
Come on.
It didn't roll actually.
Look, it's rolling right now. Yeah,
It's moving, it's just not there.
It worked like a champ this morning.
Why don't you try with a pantograph generator?
You could.
There, we got it to roll a little bit.
You say can?
So, how am I making the can roll without touching it? Involve the word torque. You don't get an answer. You have to use the word torque and not the word nothing. So you're out. Connor.
What?
How am I making the can roll and use the word torque?
Sorry.
Don't listen to Charles.
Like me to
No.
The attraction is causing a torque on the can, which
Ah,
makes it
okay.
roll.
So if you assume that this is negatively charged, when I bring that close, it's making a region on the can that is positively charged. And that small region on that can is being attracted to it, creating a torque, okay? And that torque is what's allowing that can to roll. Now, obviously, if I do this, I'm not gonna be able to pick up the can, okay? Just don't have that much of it. But if I roll that over, because it's a smooth enough surface, I can temporarily induce a small region that has a positive charge that gets attracted to it, but it's always changing as the can rolls. Okay, back we go.
Wait, hold on. How did you discharge the machine then?
This?
Like, yeah.
I just
Just touch it.
But how does that like take away the magnetic field?
No, it's an electric field. So
The electric
basically,
field.
so what's happening is that this is a weird Van de Graaff generator. Because every other Van de Graaff generator I've ever ran with in my life creates a negatively charged. This one actually creates a positive field, which is weird. So basically, it's taking electrons away from this. So when I put my hand on it, what's happening is that it wants to equalize everything out. So instead of excess electrons that flow over my body to the ground, it's reversed. So when I touch that, everything is trying to get back to being electrically neutral. So electrons are actually flowing from the ground on me over my skin, which conducts electricity very well, which is why we were able to conduct that field all the way around us. So when I do that and get close to it, then those electrons flow across, I touch it, everything equalizes out.
When you go like that, so just touching it, won't it be the same no matter what?
What do you mean?
Like when you were like discharging it, you'd like tap
Yeah.
it instead of just like.
Well, because
Couldn't you could just
I could have,
scared.
but it's just,
Can't you tap it with anything and it'll go back?
no,
No,
because you have
essentially grounded,
conductors and you have
yeah.
non-conductors. So if I touch it with a pure non-conductor, then nothing would happen. But if anything will allow that electricity to flow over it at all, then,
It goes back to
yeah.
normal. Okay.
Yep. Okay, back to you.